Convolutional neural networks. Here is the high-level architecture of CNNs. So, which has four components: the input layer, convolutional layers for feature extraction, fully connected layers for classification, and then finally the output prediction. This is a broader, big picture. And first, let's discuss about this the higher big picture. Then we will dive into the each and every one of these components. So the big picture in this, the four components. The first one is, first we feed the raw image to the convolution layers. Then the second aspect is the image passes through the convolutional neural networks, the layers, to detect the patterns and extract features called the feature maps. Then the output of this step is then flattened to a vector of the learned features of the image. And the third aspect is the flattened features vector is then fed to the fully connected layers to classify the extracted features of the image. Then the neural network then fires the node, the node that represents the correct prediction of the image. Here, in this example, we are classifying two classes, 3 and 7. Then the output layer will have two nodes, one to represent the digit 3 and the other one for digit 7. So here you can think of the feature extraction step as breaking large images into smaller pieces of features and stacking them into a vector. So after this feature extraction, once the feature extraction is complete, then we add fully connected layers, the regular multi-layer perceptron, to look at these features vector. Now let's discuss the basic components of convolutional neural network architecture. There are three main types of layers that you will see in almost every convolutional network. So the first one is the convolutional layer, and second, pooling layer, and the third component is the fully connected layer. Textually, we can say that the textual representation, we can write it like input, then it goes into the convolution layer, which again goes into ReLU, the activation function, then which the output goes to pool, and then convolution, ReLU, pool, then the fully connected layer, then finally goes to the softmax. So here the ReLU and softmax activation functions are not really standalone layers. They are the activation functions used in the previous layer. So that's the full architecture of a convolutional network. Now let's dive deeper into each of the layer types separately to get a deeper intuition on how they work. So convolution layers. The convolution layer is a core building block of a convolutional neural network. Convolution layers act like a feature finder window that slides over the image pixel by pixel to extract the meaningful features that identify the objects in the image. So what is convolution? In mathematics, convolution is the operation of two functions to produce a third modified function. To explain this definition in the CNN's context, the first function is the image, the input image. The first function is the input image, and the second function is the convolutional filter. We will perform some mathematical operations to produce a modified image with the new pixel value. Now let's zoom into the first convolutional layer to see how it processes an image. By sliding the convolutional filter over the input image, the network is breaking the image into little chunks and processes those chunks individually to assemble the modified image, and that is called feature map. Now that we are having this diagram, let's list some facts about the convolution filter. The small 3 by 3 matrix, the 3 by 3 matrix in the middle is the convolution filter, and they are also called as kernels. So in this class, we kind of interchangeably we use filter or kernels and so on. So the kernel slides over the original image pixel, I mean the pixel by pixel, and does some math calculation to get the values of the new convolved image at the next layer. The area of the image that the filter convolves is called the receptive field. So what are the kernel values? Remember, the connection weights in the multi-layer perceptron that we saw earlier. Um, in convolutional neural network, this convolution matrix is the weights. This means that they are also randomly initialized and the values are learned by the network. So you will not have to worry about assigning its values. The math goes like this. Some the same as in the multi-layer perceptron. Remember, we used to multiply the input by the weights and sum them all together to get the weighted sum. That is W1 into X1, W2 into X2, also adding all of them, and then finally add bias value. So we do the same thing here, except that in convolutional neural network, the neurons and the weights are structured in the matrix shape. So we multiply each pixel in the receptive field by the corresponding pixel in the convolution filter and sum them all together to get the value of the center pixel in the new image. This is the same matrix dot product we did in the regular multi-layer perceptron. So here you can see that 93 into minus 1, 139 into 10, 101 into 1, 26 into minus 2, 252 into 0, 196 into 2, 135 into minus 1, 240 into 0, 48 into 1, and the whole sum is 243. So the filter or the kernel slides over the whole image, chuck, 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 and then chuck, 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 chuck. So whole image, and every time we multiply every corresponding pixel element, pixel element wise, and then add them all together to create a new image with new pixel values. This convolved image is called the feature map or the activation map. So that's basically the filters concept. Now let's look at the convolution layer as a whole. Each convolution layer contains one or more convolution filters. The number of filters in each convolution layer determines the depth of the next layer, because each filter produces its own feature map. That is the convolved image. So let's look at the convolution layers in Keras to see how they work. And so here this one line of code creates the convolution layer. So we'll see where this line fits in the full code maybe later. So let's stay focused on this one line, the convolution layer. As you can see from this code, the convolution layer takes 5 main arguments. And in our early last couple of classes that we saw that the ReLU activation function is the best choice among the various activation functions. And likewise here we have chosen the activation function as ReLU, especially in the neural networks that we used in the hidden layers in the last couple of classes. So that's one argument is taken care. Now let's explain the remaining 4 hyperparameters that control the size and depth of the output volume. Here the filters, which is essentially the number of convolutional filters in each layer. So this represents the depth of its output. And the kernel size, the size of the convolutional filter matrix, sizes vary from 2 by 2 or 3 by 3 or 5 by 5 and so on. And the stride and padding, so we will explain this, both of them together. Now let's look at each one of these hyperparameters. The first one is the number of filters in the convolution layer. Each convolution layer has one or more filters. To understand this concept, let's get back to the multi-layer perceptron that we were discussing in the last couple of classes. Remember how we stack the neurons in hidden layers, and each hidden layer has a n number of neurons called hidden units. And here is the multi-layer perceptron diagram that we were discussing. And the same thing for convolutional neural networks. The convolution layer or the hidden layers. And to increase the number of neurons in hidden layers, we increase the number of kernels in the convolution layers. Each kernel unit is considered as a neuron. For example, if we have a 3 by 3 kernel in the convolution layer, this means we have a 9 hidden units in this layer. When we add another 3 by 3 kernel, we will have 18 hidden units and another one to be 27 and so on. So by increasing the number of kernels in the convolution layer, we are increasing the number of hidden units, which make out the network more complex to detect more complex patterns. And in this picture, you can see the representation of the convolutional neural network layers that shows the number of kernels idea much more clearly. The input image, convolution layer 1, then feature pooling layer, convolution layer, feature pooling layer, convolution layer, and feature pooling, and finally the classification layers. So now the kernel size. As we discussed earlier, the convolution filter is also known as kernel. The filter kernel, we interchangeably we use this terminology, and it's a matrix of weights that slides over image to extract features like this, starting from the top left. You know how you read the book textbook, we read from top left and go towards right, and then next line, and then till we reach the bottom right. So likewise the kernel goes and slides over the image to extract the features. The kernel size here refers to the dimension of the convolutional filter. So the width by height. So the common one is 3 by 3 or 5 by 5. So the kernel size is one of the hyperparameters that we'll be setting when building a convolution layer. Like most neural networks, the hyperparameters, there is no one good answer that fits all the problem. The intuition is smaller filters will capture very fine details of the image, and bigger filters will leave out minute details in the image. So remember that these filters contain the weights that will be learned by the network. So theoretically, the bigger the kernel size is, the deeper the network, the better it learns. But then this comes with a higher computational complexity, and this might lead to overfitting. So the kernel filters are almost always square in the square shape, not in general people use a rectangular shape or something. So in general these kernels are in the square shape and range the size from 2 by 2 at the smallest and 5 by 5 at the largest. Theoretically you can use bigger filters but not preferred because this will lead to losing important details of the image. Then the stride and padding. These two hyperparameters, we normally usually think of them both together because they both control the shape of the output of this convolution layer. Let's see how. The first one is the stride. A stride is the amount by which the filter slides over the image. For example, to slide a convolution filter 1 pixel at a time, then the stride is equal to 1. If you want to jump 2 pixels at a time, then the stride is 2. Strides of 3 or more are typically uncommon and rare in practice. Jumping pixels will produce smaller output volumes spatially, and a stride of 1 will make the output image roughly the same height and the width of the input image, while the stride of 2 will make the output image roughly and half of the input image size. So I say roughly because it depends on what you set the padding parameter to do with the edge of the image. So now let's look at the padding part. So often called it's zero padding because we add zeros around the border of the image. Padding is most commonly used to allow us to preserve the spatial size of the input volume. So the input and the output width and the height are the same. This way we can use convolution layers without necessarily shrinking the height and width of the volumes. So this is important for building deeper networks, since otherwise the height and height or width would or shrink as you go to deeper layers. The idea of stride and padding hyperparameters is we should be able to do one of two things. The first one is keep all the important details of the image and transfer them to the next layer. That is when stride equal to 1 and padding equal to same, or ignore some of the spatial information of the image to make the processing computationally more affordable. So now let's see the pooling layers. So the pooling layers are also known as subsampling. Uh, Adding more convolution layers increases the depth of the output layer, which leads to the increase of the number of parameters that the network needs to learn or optimize. So you can see that after adding several convolution layers, usually tens or even hundreds, this will produce a huge number of parameters, the weights. This increase in the network dimensionality will increase the time and space complexity of the mathematical operations that take place in the learning process. This is when the pooling layers come in. That is the subsampling or pooling. So which helps in reducing the size of the network by reducing the number of parameters passed to the next layer. The pooling operation resizes its input by applying a summary statistic function such as maximum or average to reduce the overall number of parameters to be passed on to the next layer. The goal of the pooling layer is to downsample the feature. Downsample the feature maps produced by the convolution layer into smaller number of parameters to reduce the computational complexity. And it's a common practice to add pool layers after each one or two of the convolution layers in the CNN architecture. There are two main types of pooling layers, the max pooling and average pool. So the max pooling, let's see that. Similar to convolutional kernels, pooling kernels are windows with a certain size that slide over the image with the stride value. The difference is that they don't have weights or any values. All they do is slide over the feature map created by the previous convolution layer and select the maximum pixel values to pass long to the next layer and ignore the remaining values. Look at this example. So here we created the pooling filter with a size of 2 by 2 and a stride 2 as it jumps 2 pixels when sliding over the image. This pooling layer reduced the feature map size from 4 by 4 to 2 by 2. When we do that to all the feature maps in the convolution layer, we get a smaller maps in dimensions width into height, that is. So, but the depth of the layer is kept the same because we apply the pooling filter to each one of the feature maps from the previous layer. So you can see in the top corner the four values, the square. So from that 1954, the maximum value is 9, and move to the next square 6478 and the maximum value is 8, and come down on the other corner, the bottom corner, 5167 and the maximum value is 7, and the last quarter 296 and 0, the maximum value from those four values is 9. So If the convolution layer had three feature maps, the output of the pooling layer will also have a three feature maps, but of shrink sizes. So as you can see here, the 4 by 4 with the depth 3 and pool layer is 2 by 2 into 3. Now, let's look at the global average pooling. This is more extreme type of dimensionality reduction. Instead of setting a window size and stride, average pooling calculates the average values of all the pixels in the feature map. And if you look at this whole 4 by 4 matrix, the average here is just 5. So you can see that the global average pooling layer takes a 3D array and turns it into a vector. So 4 by 4 by 3 becomes, after pooling, it becomes 1 by 1 by 3. So let's review how we did so far. Until this point, we used a series of convolution and pooling layers to process the image and extract meaningful features that are specific to the images in the training dataset. And if we have to summarize in 2 points, the first one is the raw images fed into the convolution layer, which is a set of kernel filters that slide over the image to extract the features. And the second point is the convolution layer has certain attributes that we need to configure. So that is given by the Keras code, which has filters, kernel size, strides, padding, and activation function. And in this filter, which is where we define the number of kernel filters in each layer, which is the depth of the hidden layer. And the kernel size, the size of the filter, also known as kernel, usually 2 or 3 or 5. And the stride, which is the amount by which the filter slides over the image. A stride of 1 or 2 are usually recommended as a good start. Then padding. That is, we add columns and rows of 0 values around the border of the image to reserve the image size in the next layer. And finally, activation, and it is strongly recommended to use ReLU activation function in the hidden layer. And the pool layer has the the pool layer has certain attributes that we need to configure. That is model.add max pooling 2D, pool size is 2 by 2, strides 2. So, and we keep adding the pads of convolution and pool layers to achieve the depth needed for our deep neural network. So after passing the image through the feature engineering process using the convolution and pooling layers, we have extracted all the features from this image and put them all in the long tube of features. Now it's time to look at the extracted features and classify the images based on the presence of these features in them. So now we are going to do that using the regular neural network architecture. That's a multi-layered perceptrons. Now the question is, why use fully connected layers? Well, the multi-layer perceptrons work great in classification problems. The reason we used convolution layers earlier is that multi-layer perceptron lose a lot of valuable information when trying to extract features from the image, because we have to flatten the image before feeding it to the network, whereas the convolution layers can process the raw images. Now that we have extracted the features, now we can use the regular multi-layer perceptron, the fully connected network, to classify these images. So now look at the diagram here. So to feed the features tube to the multi-layer perceptron for classification, we flattened it to a vector with the dimensions 1 by n. For example, if the features tube has the dimension of 5 by 5 by 40, the flattened vector will be 1 by 1000. And then we add one or more fully connected layers, and each layer has one or more neurons, similar to what we did when we are building the regular neural network. And then the softmax activation functions. That's the part of the output layer for classification problems. And when we are classifying more than two classes, the softmax activation function is the most apt one. And so here we are trying to classify digits from 0 to 9. That's the 10 classes. And the number of neurons in the output layer are equal to the number of classes. Then the output layer will have 10 nodes.